So from a scatter plot, we can get a general idea of the strength and direction of how the data is associating with each other. But what we want is an actual value, a numerical value that we can evaluate that'll tell us exactly what's the strength and the direction of the data. This value that we're going to analyze is called the correlation. In general, correlation tells how two variables associate with each other. The numerical value that we're going to look at is the linear correlation coefficient, which in terms of a symbol is where we'll use the letter little r. In fact, down here you can see a breakdown of the lowercase r represents sample linear correlation. If we had population data, which is going to be a rare case, but if there was population data, we use the symbol, which is the Greek letter rho, and that would be used to represent population linear correlation. So in calculating linear correlation, what a formula would do is it would check the association of how the x values and the y values are relating to each other. And is there this difference across the data in terms of being very spread out or very close together following this linear trend? Now, there's a lot of pieces to that formula, and I even wrote out there's 2 ways to calculate the formula down here. But the thing is, and we have the tools and resources to calculate these pieces. You can see these means, which this y bar would just be the mean of the y data. You can see these are standard deviations, standard deviation of the x value, standard deviation of y's. Over here you can see z-scores coming through in the other formula. It's not too bad to try to do it by hand, but we're not going to. We are just going to use technology to do it, because this is one of those cases where if we even did it by hand, most often due to just large data sets, it would take a long time, and just doing work by hand, it often comes out incorrect. So what we're going to do is I'll show you in GeoGebra how to get a scatter plot out, as well as getting this linear correlation coefficient. So this value for r, some characteristics that we have, it is stuck between -1 and +1. In fact, this number that we're getting out is just an index number for where it lands on this number line. And down below here, what we're going to do, I even divided this up a little bit, and we can see is one little change from your worksheet to mine is I put these dots at the end for at -1 and +1, and that's because really those arrows are incorrect. It's not going to continue on and on. R is stuck in that -1 is the least value it can be, and +1 is the largest value it could be. And then what I've done here is I divided up the number line, kind of cutting it 1/2, and then 0.8 is going to be another cutoff. Now some resources change with that, but generally this 0.8 is a good cutoff. With our value for R, we're going to think about where do we land on this number line, and what does that tell us about strength and direction. The closer we are to -1 and +1, the stronger the association is. So if I had to draw a scatter plot for this case of r equals -1, what that would look like is it would have the strongest association, meaning our data would form a perfect line. It would be perfectly linear, and with -1, how it would come through is with a negative direction to it, or negative slope. Whereas at +1, if we had a scatter plot, this would also be perfectly linear, and then from there, it would have a positive direction to it. So out at -1 and +1, we have the strongest associations, and then as we get closer to 0, the data weakens. In fact, at 0, what we would see is that case of just a blob of data without any trend or direction to it. Just kind of, the data could be anywhere. But then as we move out into those tails towards -1 and +1, the data strengthens. So as you can see from those values there, at -1 had a negative slope and +1 had a positive slope. That's where we can see the direction coming from our linear correlation coefficient, meaning if we have a value for r between 0 and +1, it's going to have a positive direction to the data. So overall, it'll be increasing. Whereas if we're between 0 and -1, we'll have these negative value for r, which implies a negative direction. So really the sign for r matches up with the direction of the data. And then if you're at 0, there's just no direction to it. There's neither direction. Then for describing the strength, so in the previous video we talked about how we could see strong, moderate, or weak, and so that closer we are to -1 and +1, the stronger the data is. So -1 to -0.8, we typically describe that as strong data. So in that area, what we would see is a negative direction, but the data should look pretty linear when we see it. So maybe something like that. Then between -0.8 and -0.5, we move into this moderate region. So what that would look like, I'm going to put this up above here, is it would still look linear, it would still be decreasing, it would just be a little more spread out. So moderately linear. And then anything between -0.5 and +0.5, we would consider weak. So in there, maybe we'd see something that's roughly decreasing, but really kind of all over the place. And then when we move to the positive side, it would turn to increasing, but if it's weak, it would still be kind of all over the place. But then we'd move back into our moderate strength. And just to fit this up above here, so something generally increasing, but is a little bit more spread out. And then anything between 0.8 +1 we'd call strong, which would look very linear and increasing. So when we get out our value for r, it'll line up with what we're seeing in our scatter plot. It's just sometimes with the scatter plot it can be hard to tell, like when is it moderate, when is it weak. But when we get out this correlation coefficient, it'll tell us exactly where we're landing. So let's go back to that cricket data, and what we'll do is look at finding r. And I will show you, here's kind of steps lined out for how to use GeoGebra to do that. So let's hop over to GeoGebra. And we're going to go to GeoGebra Classic and that spreadsheet that we used for one variable analysis previously. So before, what we worked with is a single column of data, and then we used the histogram button and did one variable analysis, and we could get out histograms and dot plots. What we're doing now is moving to two variable regression analysis, and you can even see our scatter plot on the side there. So what I'm going to do is plug in the data. So here's our cricket data. You take all of your x values and plug them into one column, and then the matching y values, and just make sure they line up. Like I was saying, with these values, they match up in terms of a single observation. So when we had 89 degrees, they recorded the 20 chirps per second, so on and so forth. So what we need to do is highlight the data. So I'm going to highlight it, and then I'm going to go to that histogram button, and then we're going to run two variable regression analysis. And with that, what will automatically open up is our scatter plot. So this will be a way, if you don't have to draw the scatter plot by hand, but you want to see how does the data graph, you can make it here. If you even need a scatter plot, you could make it here and then copy and paste the data. So from there, we can see our scatter plot, and then we want to use that show statistics. So similar to how we found mean and standard deviation before, same idea here with that summation x symbol. You're going to click that for show statistics, and that'll give us a bunch of data over here. So you'll see the mean of the x values, so just that first column A, the average, the standard deviation of those. And then for the y values, which is column B, you can see their mean and their standard deviation. We're going to focus on is r. And you can see that symbol for rho down below, but we have sample data, and pretty much each time we do this using sample data, so we're only going to use R here for that 0.8135. So for our first question here of what is the correlation, that would be asking what is R with a 0.8135. A good thing to do when you check out that scatter plot is make sure that it looks roughly linear. We looked at that data already, but if that data came through and it was obviously curved, we'd want to be careful because this value for R is strictly for linear cases, or at least roughly linear cases. So with that, if you see curve in our data, it's kind of like checking conditions for can we move forward with our data, and if it was curved, we could not. But we saw something that was roughly linear, so we can use this value for R. So describing the association. So describing association, we want to think about direction and strength. So I could say is the association between chirps per second and temperature is, and then I want to describe direction and strength. So what we can do is take this 0.8135 and see where are we landing on this number line here. So 0.8135 is landing here. It's a little above 0.8. So with that, we could see where are we lining up. This will be strong and positive. So the association that we're seeing between our two variables is strong and positive. So with that, we can get a sense of how linear is it, or how strong is this relationship, and then positive gives us an idea of increasing one of those variables typically leads to the other variable increasing as well. So do these results confirm that the increase in temperature leads to a higher number of chirps from crickets? So I threw this wording in here because it's getting at that cause and effect idea again. This is implying causation. One increase leads to another, and we still can't. Even though there's a strong association, there's still a chance of lurking variables. So we could say there's a strong association, but we can't talk about changing one leading to a value for the other. Okay, while we're talking about R here, there's something else that we can evaluate with R, which is R squared. And sometimes you'll see this written as capital R squared, and even up above, you might sometimes see like capital R equals 0.8135. There isn't a difference there. It's just some resources use capital R, some resources use little r. So both of those are sample linear correlation coefficients. So same thing. So I just want to show you that notation just because it kind of switches back and forth. So they're not very consistent with it. But the key is this coefficient of determination, which is a very fancy wording for just taking r and squaring it. What it does is it tells us the percentage of variation in the y values that can be explained by the least squares regression line, or in fact, let me give us another kind of sentence structure here. It's the percent of the variation in y that can be explained by x. So it's another way of relating the strength of the data. So it's how much of y changing is coming from the change in x. So going back to our example with the crickets, and we found r is 0.8135. So if we wanted to find this coefficient of determination, we would take r squared, which would come from 0.8135 squared, which would be 0.6618. So how I would fit this into a sentence is that this number is a percentage. Now be careful, because only r squared is a percentage. When we have R, there are no units there. It's just an index number to land on that number line between -1 and +1. So R itself doesn't have units. When we square it, it's a percentage. So the sentence I would make here is 66.18% of the variation in Y, which in our case is the chirps per second. So percent of the variation in chirps per second can be explained by X, which is temperature. So it's coming through here is we have this strong association, which leads to this high percentage of how these variables relate to each other, and how changing one is influenced by the change in the other, or how Y is responding to changes in X. So in this case, it's 66.18% of that change in Y is coming from X. And what you'll see is with weaker correlations, so say we have the weakest correlation, say R was 0, well then R squared would also be 0. So that would lead to like 0% of the change in Y is explained by X. And that just reinforces this idea that they're not relating to each other at all. This would be a case where our scatter plot just doesn't have any trend. So what we're bringing through there is this idea that how Y changes, 0% of that change is coming from how X is changing. So totally not related at all. Whereas if we go to the strongest correlation, say we had R is +1, well, or I wrote -1, either way I guess would work, but if you square that, it would also be 1. So our sentence would come from 100% of change in Y is explained by X. So this +1 case makes that straight line. And what that sentence is bringing through is in terms of how Y changes, 100% of that change is coming from how X changes. Because if we increase X by 1 or whatever unit that is, Y is going to change the exact same amount each time. So they're directly related to each other. So this coefficient of determination is another way of describing the strength of the data. Typically what you'll be doing with correlation is these steps of using GeoGebra to find R. So we're going to skip that formula for calculating R and just grab it from GeoGebra. And then you'll want to use this number line here and figure out where are you landing to get a description of direction and strength. So you'll get these two descriptors for association.